So students, in this chapter we're going to learn about thermodynamics and thermochemistry. Sandeep is here with us and he's going to take us through various concepts and theory of the same. So Sandeep, can you tell us what exactly is thermodynamics?
So, welcome to the world of thermodynamics. First, let us see what is the definition of thermodynamics, basic definition. Thermo means heat, dynamics means motion. So, thermodynamics itself says us that it is transfer of heat
Right.
from one system to another.
Right. And what exactly is thermodynamics based on?
So, thermodynamics, it is totally based on three laws or three generalizations. And these three laws, they are totally based on human experience, and we don't have any practical proof for it. And we call it as first, second, and third law of thermodynamics.
Right. So that is thermodynamics. What exactly is the difference between thermodynamics and thermochemistry?
So in thermochemistry, we are too specific. We'll be learning about the heat involved in reactions. Suppose that we are dealing with a reaction A plus B, which gives product some C or D. So in this reaction, whether heat is evolved or heat is utilized for the reaction.
Okay, so transfer of heat in chemical reactions.
Chemical reactions, exactly.
Right.
So now let us learn about basic terms in thermodynamics. First, let us see what is a system. In thermodynamics, system is something that which one we are interested in.
Right.
Suppose that we are making a reaction in a beaker.
Exactly. Yeah.
Right. So in this system, we are mainly interested only in this on this beaker. So we neglect about the surroundings, right?
Okay.
Or the rest part of the universe. So the remaining part of the universe we call it as surroundings, and the system that we are interested in, that we call it as system.
Okay. So what kinds of systems exist in the nature?
See, there are three types of system. One, it is open system. In open system, we have both heat and mass transfer.
Right. Like a cup of tea probably.
Exactly. Suppose if you take a cup of hot water, hot tea.
Yeah.
See, in this system, heat will be escaped from this hot tea.
Exactly.
Right. So
Yeah.
there is heat transfer.
Yeah.
And because of the surrounding air or a movement of air, water will also escape from this system.
It'll evaporate. Yeah.
Yeah. So we have both mass and heat transfer, which make it as an open system. Right. Now, second system, we call it as closed system. In closed system, name itself says that there is no mass transfer, only heat transfer.
Okay.
Can you name an example? Can you give an example for this?
A pressure cooker probably.
Yes, exactly.
Right. Because only heat transfers, no mass transfers.
In a pressure cooker, only heat will be transferred. Since see, take a pressure cooker, will be supplying heat Q.
Yeah.
But there is no mass transfer in the system, so we call it as closed system.
Right. Right.
And the third system is adiabatic system. We call it as isolated system also. See, actually these kind of systems, they do not exist in nature. We just assume that they will exist.
So it is not practically possible to have an adiabatic system.
Exactly. So adiabatic system, it is the third system. Guess it. See, in first one you are having both mass and heat transfer. In the second system closed, we have only heat transfer but not mass transfer.
Yeah.
So third one will be
no mass and no heat transfer.
Exactly. So
Right.
isolated system, it is a system where we don't have heat or mass transfer.
Okay.
So these kind of systems, they do not exist in nature. We just assume that there are some systems which are adiabatic or isolated. Fine.
Yeah.
Now let us see some basic properties of the systems or some variables. See, there are two properties. One is extensive property and the second one is intensive property. Right. See, extensive property is something that which depends upon the matter or the mass present in it. So extensive property depends on
The matter.
present. And what about intensive property? It doesn't depend upon the
Matter.
matter present. Let us take an example. Suppose that take 1 kg of sugar.
Yeah.
So add few grams of sugar to it. So now the mass will change.
Exactly.
So mass, it depends upon the amount of matter present in it.
So it becomes an extensive property. Okay.
Now,
So can you name some other extensive properties?
exactly, volume, it is an extensive property.
Right. It depends on the matter present.
Matter
Yeah.
present. And internal energy. Actually, internal energy, it is total amount of energy present inside the system.
Okay.
So we'll talk about it later.
Okay.
So internal energy, enthalpy, entropy,
Okay.
these all are extensive properties. We'll talk about these properties later.
Okay.
And coming to intensive properties, suppose take temperature. It is an intensive property. Take a hot rod with a temperature T. Now break that hot rod into 2 parts. So will the temperature change for both things?
No, it won't.
No, right. Temperature will be same for both the things.
So it'll be an
Initially we have
intensive
mass m. Now mass is m by 2 for each one. So it doesn't depend upon the amount of matter present inside it.
Right. Right.
So it is an intensive property. And some other intensive properties are pressure and density, since
Right.
density is mass by volume,
Exactly.
and
So it's like
specific heat.
dividing one extensive property by another makes it an intensive property.
Exactly.
Makes the whole an intensive property.
Exactly.
Okay.
Specific heat. Suppose that if you are dealing with a reaction, some heat is evolved from the reaction.
Okay.
Now, if you are calculating heat evolved per unit mass of reactants,
Haha.
so it makes it as specific heat.
Okay.
Whenever
Okay.
we are telling specific, in the sense that we are dividing by unit mass.
Okay. Okay.
So it doesn't depend upon the amount of matter present in it. So we are always talking about the unit mass systems, right? So
Yeah.
it is an intensive property.
Okay. So how can you tell the difference between an extensive property and an intensive one?
See, as we talked in this temperature example, remove some matter from the system. Check whether that property is changing or not. If
Yeah.
the property is changing, then it is extensive property.
Right.
If it is not changing, then it is
Intensive property. Yeah.
right. Since extensive property depends upon the amount of mass present in it.
Okay. Okay.
Fine, right? Now let us talk about state variables or state functions.
Okay.
See, actually, these properties depend upon the only on initial and final states on the system, but doesn't depend upon
Okay.
how they are reached.
Okay.
Suppose I'll tell you an example.
Yeah.
You want to go from first floor to 10th floor of a building,
Right.
so you can go by elevator
Exactly.
or you can climb by steps. So is the work done by you same in both the cases?
It is not. I work more when I've climbed the stairs.
Exactly. Right. So work done, it depends upon the path.
Yeah. Yeah. It does.
Right. So it is not a state function. What did we tell about state functions? Actually, these properties depend upon the initial and final states of system, but they are independent of path.
Okay.
Right.
But if we were talking about what number of floor you are on,
Exactly.
irrespective of how you got to the floor.
So I can go from first floor to 10th floor directly,
Hmm.
or I'll stop in second floor.
Yeah.
I'll climb by steps from third floor.
Yeah.
I
And
can
then
go
you'll
by
take a
different
lift.
parts, right? But
Exactly.
finally I'll reach 10th floor.
10th floor. So it won't be a state variable.
Fine.
Yeah.
Right. So some examples for state variables are pressure,
Right.
temperature, enthalpy,
Entropy. Yeah.
and internal energy. These
Okay.
all are state functions. In the sense, they doesn't depend upon how they are reached.
Okay.
They depend upon on that particular state itself.
Yeah.
Fine, right.
Correct.
So they are state functions. Now we'll talk about thermodynamic equilibrium. So what is thermodynamic equilibrium?
Hmm.
A system is said to be in thermodynamic equilibrium when it shows no further tendency to change its property with time.
Okay.
Suppose that we are having a system and properties of the system are not changing with time. then it is in thermodynamic equilibrium. So thermodynamic equilibrium, it is a combination of three equilibriums. One, it is in chemical equilibrium.
Yeah.
Two, it is in mechanical equilibrium. And three, it is in thermal equilibrium.
Okay.
So if the system is in combination of these three equilibriums, then we can tell that it is in thermodynamic equilibrium state.
Yeah.
Fine, right? What is chemical equilibrium? In the sense, compositions of the system is fixed, so they are not changing with time.
Okay.
Suppose that in a system initially we have 1 mole of something.
Okay.
So that 1 mole composition is fixed. It is not changing with time.
Okay.
So then the system is said to be in chemical equilibrium.
Ah.
What is mechanical equilibrium? When there is no work is done by the system, then we can tell that it is in mechanical equilibrium. Or else we can tell that when pressure is constant.
Right.
It is in mechanical equilibrium.
Correct.
So mechanically it is not doing any work. Right. Now what is thermal equilibrium? So name itself says that when temperature is constant,
the system is in a thermal equilibrium.
Thermal equilibrium. So when the system is in combination of all these equilibriums, we can tell that it is in thermodynamic equilibrium. Right?
Yeah.
Now we'll talk about few thermodynamic processes.
Okay.
What is a thermodynamic process? When a thermodynamic system changes from one state to another, this operation it is called a process.
Okay. And what kinds
Fine,
of processes
right?
are there?
See, initially the system is at particular temperature and pressure P1 T1. Now it is changing to P2 T2.
Okay.
The system is changing its state, right?
Yeah.
So the way it is changing, we call it a process. Thermodynamic process.
Okay.
Fine. Now we'll talk about few thermodynamic processes. The first one is isothermal. Isothermal. The name itself says that temperature is constant in this process.
Okay.
Right? Suppose that we are having a system at P1, B1, T1, and at a constant temperature we are changing property of the system.
Okay.
Now we are making it T1, B2, P2.
P2. Right.
But at constant temperature. Right? This is an isothermal system.
Yeah.
Now, physically, how can we make this isothermal system? Suppose we are making a reaction.
Yeah.
Put that reaction in constant temperature water bath.
Okay.
Surrounded by water at some 60 or 70 degrees centigrade.
Okay.
So now total system is maintained at a particular temperature, right?
Yeah.
For the whole process.
Mm-hmm.
Temperature is constant. So we call it as isothermal system. Now we talk about next process, adiabatic process.
Which we've already talked about.
Exactly. What is adiabatic process? No heat exchange occurs.
Isolated.
Yeah, isolated. That
exactly.
is adiabatic system.
Yeah.
It is isolated.
Exactly.
So, no heat exchange occurs.
Exactly. Yeah.
In the sense, we are not supplying any heat to the system, or we are not taking any heat from the system.
Okay.
Right? We call it as adiabatic process.
Mm-hmm.
Fine. Now the third one, isochoric process. Suppose that we are changing the state of system from one thing to other by maintaining at a constant volume. We call it as isochoric process.
Okay.
It is at constant volume.
Okay.
And now finally, isobaric process. Guess what can be isobaric process?
Isobaric process.
Yeah,
Pressure doesn't change.
exactly. Isobaric process, we maintain a constant pressure in the system.
Okay.
Suppose that we take a beaker, we put some piston with some fixed weight M, and some reactions are going inside the system, but they are maintained at a constant pressure.
Okay, the
We call
system
it
pressure
as,
isn't changing.
Yeah, it is an isobaric process. Whatever changes are occurring.
Okay.
Right? Now, suppose if the system is going from particular state P1 V1 T1 to P2 V2 T2 and finally reaching to the same initial state. So it is a cyclic process.
Yeah, it is.
So we call these kind of systems processes as cyclic process. In the sense we are reaching initial state.
And what is the speciality of this process? What properties remain the same?
Wherever we are starting, we are finally coming to the same state.
Right.
This is P, this is V. Suppose we are starting here, we are going in different process, finally coming to the same state, right?
Yeah.
So finally, pressure, volume or temperature, all will be same.
Yeah.
So this is cyclic process. So we'll talk about work done in cyclic process and about enthalpy, entropy later. Fine, right? Suppose that previously we talked about state functions, right?
Yeah.
What is a state function? It doesn't depend upon the path. So
Yeah.
it depends only on the state of that property. If you
Right.
take enthalpy, initially we are at this position. Finally also we are at the same position in the cyclic process. In the sense, there is no change in enthalpy.
Exactly.
So change in enthalpy equal to 0 in the cyclic process.
Correct.
Fine, right? So for state functions in cyclic process, change will be 0.
Okay. So similarly for
Previously we are talking about different thermodynamic process. Now we'll continue it. See, suppose that we are having a system. We can change the state of system from one state to other either reversibly or irreversibly.
okay.
Suppose that we are having a beaker, a piston. It is at volume V1
Yeah.
and now we want to change that system into volume V2.
Right.
Suppose if you put a 10 grams weight on it.
Yeah.
In other case, I'll put 10 1 grams weight on it. Right?
Okay.
In first case, I'll take 10 grams weight directly.
Okay.
Now it will reach to system of volume V2.
Okay.
Now in the second case, I'll remove 1 gram each.
Okay.
So at first instant, after taking 1 gram, it will reach volume V1 dash.
Okay.
Second instant, it will reach V2 dash after taking 1 more gram weight. And finally, after taking all the weights, it will reach volume of V2.
Yeah.
What is the difference in these two processes? See, in the first case, we are directly removing this 10 grams weight.
Okay.
And the system is, a process is very fast. In the second case, we are removing it very slowly. Means we are changing the state of system very slowly. So this one is a slow process.
Okay.
So at every state, the system is attaining equilibrium. So we call this process as a reversible process.
Okay. So how do you get to know in a question?
Fine. See, if in the question, if the process is given to be very slow, if it is given as a slow process, implies that it is a reversible process.
Yeah.
Or if it is given as some fast process, make sure it is irreversible.
Alright.
Fine. Now we'll see about the work done in these two processes.
Okay.
What is work done? Work done is force into displacement, right?
Yeah.
See, force is pressure into area.
Yeah.
So work done is pressure into area into displacement. So area into displacement gives us volume.
Okay.
So work done is pressure into volume. Fine, right? Now we'll see work done in two processes. One in reversible case, other in irreversible case. We'll check PV graph. Since work done is pressure into volume, so it will be area under this PV graph.
Okay.
So in first case, irreversible. Second one is reversible case. Fine, right? See, in the first case, we are taking system from P1 V1 to P2 V2.
Okay.
Suppose that P2 is at 1 atmosphere. We removed all the weights, right? It is at atmospheric pressure. In this process, since work done is pressure into volume, so work done will be area under this graph.
Correct. Yeah.
It is a fast process, right? So pressure will be 1 atmosphere at every
Yeah.
instant. So work done will be area under this graph, 1 atmosphere into this one.
Correct.
But in the second case, P1 V12, P2 V2. After removing 1 gram weight, it will attain new state V1 dash.
Right.
After removing 1 more gram, it will attain 1 more new state.
Yes.
So work done will be area under this graph at each instant,
Okay.
right?
And the total would be addition of all these.
Yes, exactly. So what can you say from this? Work done in reversible case, is it greater than or less than?
It's less than work done in reversible case.
Yes. No, work done in reversible case is more than work done in irreversible case.
Yeah.
Check the area under this graph,
Yeah.
right? Fine. Now we'll talk about internal energy. What is internal energy? Suppose that we are having a system, we have some gas inside that system.
Yeah.
So these gas molecules will be having some kinetic energy, some rotational energy for each molecule, some vibrational energy, potential energy, everything, right?
Correct.
So by summing up all these energies, we get internal energy, U.
Okay.
So internal energy, it is nothing but sum of all energies of the system, right? So some key points to remember for this is, see, internal energy, it is an extensive property. Previously we defined extensive property, right?
Yeah.
If it depends upon the amount of mass, it is extensive property.
Exactly.
See, in this case, if we increase more amount of mass, in the sense it is carrying more amount of energy.
Right.
So internal energy depends upon mass, so it is extensive property. Second case, it is a state function,
Yeah.
right? So it depends only on the state, it doesn't depend upon how you reach that state, right?
Correct.
So it is a state function. And see, for ideal gases, internal energy, it is only function of temperature, it depends upon only temperature. So remember
Right.
these things. And see, now we have energy in the system, how can it escape? See, energy can escape from the system only in two ways. Either it can reject as heat, or it can do some work.
Exactly. Yeah.
So from this we got first law of thermodynamics from this correlation. Fine, we'll talk about first law of thermodynamics in the next part.
Okay.
Now we'll talk about first law of thermodynamics.
Right.
See, as I told previously, that energy can escape from the system either as heat or it can do some work.
Yeah.
Right. So first law of thermodynamics states us that dq equal to du plus dw.
All right.
So du is change in internal energy, dw it is the work done by the system, and dq it is heat entered into the system. So let us talk about sign convention for this formula, using this formula.
Right.
See, in chemistry, mainly in thermodynamics, we'll deal that, see, anything that enters into the system, we take it as positive.
Right.
Anything that goes out of the system, we consider it as negative.
Yeah.
Fine, right? Suppose that we are heating this system. What should we keep? Q as positive or negative?
It's coming into the system, should be positive.
It is positive, right?
Yeah.
Suppose that system is doing some work, it increasing its volume, it is
Yeah.
doing some work. So is it positive or negative?
Work done is negative.
Yes, exactly. It is going out of the system, right?
Yeah.
It is negative.
It's done by the system.
By the system.
Yeah.
So work done on the system will be positive, and work done by the system will be negative.
Yeah.
Right. Remember this sign convention, and this is somewhat different from what you learn in physics. So
Yeah.
remember this. So anything into the system, positive.
Actually, the physics thing is also the same. It's only the equation that differs.
Exactly.
convention
Exactly.
that also
Don't
changes
get confused
accordingly.
with it. That's what I mean.
Yeah.
And anything out of the system, negative. Fine. Right. And we know about what is internal energy, We
Yeah.
talked about it. And what is work?
Yeah.
Work is nothing but mechanical work, that is
Right.
pressure into volume. Fine, right? Now we talk about enthalpy, a new term.
Okay.
What is enthalpy? See, in chemistry, most of the reactions we do it in open vessels, right?
Yeah.
So open vessel in the sense we are doing reactions at 1 atmospheric or atmospheric pressure.
Which is constant.
Yeah, they are constant pressure processes. Fine, right?
Hmm.
So at constant pressure, from first law of thermodynamics, we know that dq equal to du plus dw.
Yeah.
What can be work done? Work done is pressure into volume. Since pressure is constant, dq equal to du plus dw.
Yeah.
So work done is delta u
Hmm.
plus p delta v,
Yeah.
which is work done, right?
Right.
So since this pressure is constant, we call this whole term as enthalpy.
Okay.
So enthalpy, it is nothing but heat evolved or heat into the system,
Right.
but it is under constant pressure. For making our calculations simpler, we just introduce this term, that's it.
Correct.
Just don't confuse with it. Fine, right? So delta H equal to delta U or delta E. Internal energy, we can either use it delta U or delta E,
Okay.
plus P delta V, or since we know that PV equal to nRT, we can mention it as delta N RT if we are dealing with gases,
Right.
right? So this is basically about enthalpy. And
Correct.
now we'll see, suppose in an isothermal system, what happens for first law of thermodynamics equation.
Hmm.
We know that delta Q equal to delta U plus delta W.
Yeah.
Isothermal in the sense constant temperature. Previously we discussed that internal energy depends only on temperature,
Yeah.
right? So at constant temperature internal energy will be constant, right?
Constant.
So
yeah.
change in internal energy will be
Zero all the time.
zero, exactly. So first law of thermodynamics becomes delta Q equal to 0 plus delta W. So work will be done at the expense of heat,
Correct.
right? Or else suppose that you are doing some work on the systems, it will be stored as heat inside the system.
Okay. Okay.
Fine,
So all the heat that you provide to the system will be converted into some mechanical work.
that's it, exactly.
Right.
At constant temperature
Yeah.
in isothermal systems,
Hmm.
right? So work done, since we know that work done is PV, PV
Yeah.
is nRT,
Yeah.
right?
Yeah.
That is for ideal case.
Hmm.
So for work done, we have one formula, 2.303 nRT log V2 by V1.
Okay.
See, they all are reversible work, right?
Uh-huh.
So we need to calculate at each and every instant.
Right.
So we'll be integrating integral PDV.
Yeah.
So
Correct.
PDV nR dt.
Right.
So by changing these things, we'll get these things, right? Minus 2.303 nRT log V2 by V1. Remember this formula.
Right.
This will be useful in calculations of work done in isothermal case.